Who is the one who has connected now? Satvik, send the link in the this thing, the summer
No,
school group
can you see it in the live?
streaming
I
link.
cannot copy the link. Where will be the link? I started the live stream, but it's not coming in YouTube.
Yeah, like you have to share this link, right, to others.
Sagar, can you once check the link I sent in the chat box?
Yeah. I'm just checking that. Yeah, I can see it, bro. I'll share it.
Okay.
Mm. Yeah, just sending it to the group. I have sent it now. I think the live works.
రేటింగ్ అంటే ఆలోచించండి ఇండియన్ వన్ యొక్క లెగసీ ఒట్టి మీద తంతే ఇది మార్క్స్ పడింది ఇండియన్ టూ
Am I audible? So hello everyone. So welcome to summer school conducted by Electronics Club. So I hope you all are excited to be a part of this program. So yeah. So we will be having many sessions to explore different areas of electronics. So we will be covering theory for the first few days, and after that we will be having a project. So we will be doing that project together. So even if you are completely new and a beginner, it's okay. Like this is beginner friendly sessions. So yeah, let's move on to today's session. So in today's session, we are going to learn about IoT, which means Internet of Things. So many of you might have heard this term before. Even if you haven't heard about it, it's okay. There is nothing to worry because this is very beginner friendly. So by the end of this session, you will have a clear understanding on basics of IoT, how it is working, and what all components are involved in it. So yeah, even if you haven't heard about IoT, we all have actually used it even without realizing it. So there are many examples around us. Like the main example is the street lights. So you all have noticed that street lights automatically turn on when it becomes dark or when it's cloudy and all, right? So yeah, it is actually sensing its surroundings. It is detecting the light, how much light is available, and it's automatically operating. So there is no human intervention there. Similarly, there are some refrigerators, smart refrigerators and all. So it have a digital display in front of them. So it shows the temperature of the fridge. And some smart fridges also show what and all are there inside the fridge, what and all groceries you need to buy, or what and all things you need to buy and all. So there are smart fridges, and many of you might have controlled AC or TV from your mobile phone without actual remote. So that is also an IoT based technology. So there are many IoT based technologies in our day to day life in nowadays. So what exactly is IoT? So in simple terms, I can say that IoT is a network of physical devices. So these physical devices are connected through the internet. So these devices actually collect the data from our surroundings. So they use sensors for this purpose. And this collected data is shared through the internet, and it will perform actions automatically. So there is no human intervention needed. So it will collect the data, it will process that data, it will communicate with other devices over the internet and take whatever actions are needed, and it will do it automatically. So that is IoT's definition. So yeah, like imagine the time before IoT. Like if there is Alexa in your home, you don't have to like get up from your bed, go near switchboard and turn it off manually. Like you can just command, okay, turn off the light, and it's off. So it just helps us to become like lazy, and it makes our life easier also. So yeah, now we understood what IoT is, like what is the definition. So to understand how it actually works, so we can see the architecture of IoT. So I will be using an example to explain this and to make it understand much more better. So imagine I'm a farmer. So I'm not a full-time farmer. I'm also doing some part-time job. So I can't be in the field all the time. So I can't check and water my plants every time manually. So what I'm doing is I'm installing a IoT-based system in my field. So I need my system to have sensors to detect the moisture level of the soil, what is the temperature of my surroundings, how much sunlight is available. And based on all this, I need to decide whether the plant needs water. So whenever required, whenever the plant needs water, the water pump should automatically on. So it should not wait for me, right? I am in my office, I am working, I can't manage this. So I need a IoT which will manage all these things. So the first thing to ensure to implement such a system is sensors and devices. First layer is sensors and devices. So I'm sure you all know what sensors is. So sensors, it collect data from surroundings. So there are different types of data. It may be pressure, temperature, light, motion. So there are different kind of sensors to measure different types of data. So in my case, I need a soil moisture sensor. I need to know how much moisture is there in my soil, right? And I need to detect the temperature of my surroundings. And also I need to know how much sunlight is available for my plants. So based on all these only I can take information, take decisions. So I need all these information. So I will be using sensors to collect that. Then the next part is devices. So devices is actually the components which perform the actions. Like here, my action is to turn on the pump, right? So my device will be a switch to turn on the pump. So devices are the physical components that perform action. Sensors are the one which detects the surroundings and take data from surroundings. So yeah, the next layer is data processing. So this layer is done by microcontrollers. So to do this, we have our microcontroller. So microcontroller is actually the brain of our IoT system. So the sensors will collect the data and it will be sent to the microcontroller for processing. So for example, if my soil's moisture level is below 30, I need to turn on the water pump. So the sensor will send the moisture level and the microprocessor based on the already decided logic, or I will have a logic, right? I will have an algorithm for the processor to take decisions. So based on that, it will take a decision and it will decide whether we should water our plants or not. So this microcontroller's job is to process the data and make decision based on the program. So that is the second layer, and the next layer is connectivity. So now imagine I'm in my office, okay? Based on the already decided logic, I don't need to water my plants currently, okay? There is enough moisture content in my soil, sunlight is also okay, temperature is also okay, and by that conditions, I don't need to water right now. But I am deciding, okay, after this time, there won't be water availability, so I need to manually on the pump. So I'm in my office, I can't come and on. So what I need to do is I need to give command from my office and the devices should act. So I need a connectivity between my devices and my mobile phone, right? So connectivity is one of the important layer of IoT system. So we ensure the connectivity using technologies like Wi-Fi, Bluetooth, 4G, 5G, LoRa. So I'm sure you have all know about this, but LoRa you might be hearing for first time. So LoRa is similar to Wi-Fi, but it's like uses low power and it covers much more longer range. So connectivity is important for exchanging the information between the devices and all. Then the next layer is user interface. So this is the part where we actually see. So we actually, it may be in our mobile phone, or I already said about smart fridges, right? So in front of the fridges there will be a digital screen. So that is also a user interface. So it is the part where we actually monitor and control them. So in my case, if I'm in my office, in my website, my user interface, I need data about like how much moisture content is there in my soil. It should show how much sunlight is there, what is the current temperature, and I should also have an option to turn on and off the pump manually. And it should also show the current condition of my pump and all. So I need a website like that, or to monitor from my office, right? So that is the another important part. So yeah, this is how IoT works. These are the four important layers of IoT. Yeah. Now we understood how IoT works, right? So the most important component is microcontroller. So microcontroller is like the brain of our IoT system. Like it's what controls our whole system, whole circuit. So it receives information, it read input from our sensors, and by using that data from sensors, it will process that information, it will control the outputs, and all those works are controlled by our microcontroller. So microcontroller is the device or the component that tells every other devices what to do. So it's one of the important part of our IoT project. So you all have heard about microprocessors, like in our laptops and all, we can see some stickers like Intel and all referring to the microprocessor. But don't get confused between microprocessor and microcontroller. Like by the name and like by seeing them, you might think they are same, but like they are designed for different purposes. So microprocessors are actually use in our devices like laptops, smartphones and all. So laptops and smartphones, we use it for different purposes. Sometimes we are gaming, use it for gaming, sometimes for streaming, watching videos and all. So we use it for many purposes. So we need to have a processor which can handle that much amount of complexities, right? So we will have a microprocessor in that case. So microprocessor is very powerful actually, but it cannot stand alone. Like it doesn't have its own memory, or it doesn't have an input output interfaces and all. So we need to, for it to function as a full system, we need to add many external components like RAM for memory, storage devices, input output controllers. Yeah, and many other supporting circuits is needed for it to work as a system. But whereas microcontroller is actually like a small computer inside a single chip. Like it already have a processor, memory, input output interfaces and all, like everything is inbuilt into a single chip. So that is how microcontroller works. But microcontroller is designed for a specific task. Like in microprocessor, it can be used for many complex functions, but microcontroller will be designed for a specific task. So that is the main difference between microcontroller and microprocessor. Okay, now the next obvious question is, how are we actually communicating with the microcontroller? Microcontroller, we actually have pins. This white color things which you can see, they are the pins of microcontroller. So there are many pins for a microcontroller. So each pin will be having a specific function. So some pin will be for receiving input, some will be for giving output, some will be for ground reference, power, to give power for our microcontroller. Some will be to establish communication protocol. So there will be many pins for different functions. And these pins actually interpret data as voltages. Like there will be voltages at the pin's end, right? So that voltage level is interpreted as data. So that is the language of microcontroller. Now there are two types of signals. Like there will be analog signal and digital signal. So digital signals is like there will be only two states. It's either off or on. Like it's either 0 or 1. Only two states will be there. There won't be any intermediate states. So in some microcontrollers, low voltage is 0 and high voltage is 5. In some microcontrollers, low voltage will be 0 and high voltage will be 3.3. So it depends on the microcontroller, but yeah, there will be only two states in digital signals. But analog signal is actually continuous. Like there is no 0 and 1. It's like a range of values. Like it can be 0 0.1, 0 0.2 and all. So in case of temperature sensor and all, imagine I'm connecting a temperature sensor to my microcontroller. So we know temperature is a continuous data. So this temperature sensor's output will be like voltages like 0 0.8, 0 0.3. Like it depends on the temperature, right? So it need to be a much more detailed. It can't be 0 or 1, right? It need to be a much more detailed thing. So yeah, that's analog signals and digital signals difference. So yeah, the next topic is analog to digital converter. So actually, many sensors produce analog signals. Like I already mentioned about temperature sensor. Like temperature is a continuous data. So I need a analog signal. I get analog signal from that sensor. Similarly, pressure, humidity level, everything is like analog, right? So the microcontroller actually perform calculations digitally. So these analog signals, analog sensors are giving us analog signals, but our microcontroller need digital data. There will be analog to digital converter in between this to convert this. So in many microcontrollers, it will be inbuilt. So we don't need to add an analog to digital converter extra and all. There, it will be inbuilt inside the microcontroller, and it will convert our analog signals into digital data for microcontroller to process. So the next topic is communication protocol. So Tejas will carry on with this topic.
So I hope my screen is visible. So hello all. So now we are going. So today we are going to see about the communication protocols UART and I2C. So before going inside these protocols, we must know something about the clock, because many communication protocols that are wired use clock. So what's a clock? Clock is just a signal that goes from high to low and low to high. So that is the job of a clock. It just does that repetitively. So this is the logic high and this is the logic low. This is the rising edge and this is the falling edge. It is used. It is a vital part in many sequential digital circuits and in many communication protocols. So speaking of sequential circuits, it is so you see that the output's present state will depend on the previous state. So I'm not going to speak about that. That would be done in the second session. So we are going to deal more about the communication protocols. So in communication, we must ensure two things for in wired communication that we are going to see. We must ensure two things: that the receiver must know exactly when the transmission is going, when the transmission has started, and second, when the and second is that the receiver and the transmitter must uh, be in par with the speed. I mean that the receiver must not be too slow or too fast for a good communication to happen. So the clock plays a vital role in that. So many communication protocols use a clock for that. So first we go about the UART protocol. It's a protocol that doesn't use a clock. So it is a serial communication asynchronous protocol. Okay, there are too many terms here. So what is a serial communication protocol? It is a protocol in which the communication happens through one wire, one bit at a time. There are the other type of protocol is called a parallel communication protocol, in which multiple wires will be used so that multiple bits can be transmitted at the same time. So this is how in the serial communication protocol of UART we use the connection. If assuming this is the device that will do the transmitting of data from to this device, then the TX of the transmitter should be connected to RX of the receiver. And if we want this device also to speak with this device, then we need to do the reverse. So, and it is a must that we connect the grounds. We must connect the grounds because we must make sure that the potential zero is constant for both the devices we are dealing with. Otherwise, the bit high state of TX may not be recognized in this device because of the different potential of grounds. So this is a must. This is the connection we need to make. And what the thing about asynchronous protocol is, it is a protocol that does not use a clock. That is the meaning of asynchronous. So how do we make sure the two things to happen? How do we make sure that the receiver knows when the transmission has started, and also how the transmission and receiving speeds are equal? So we'll go into that. So for that, we make the bits make the bits in a frame. Put the bits in a frame with starting with the start bit and put your data bits here. You can keep 5 to 9 of the data bits here, then followed by the parity bit. This bit is used for error checking in these data bits, and this is as there may be noise accumulated in these bits, we are using this, but it is not a very standard error checking wave as because if we use parity, we'll know if there is an error or not, but we won't know where the error is exactly. Then we have to stop it. So the receiver will know when the transmission has started by the start bit. So when the transmission is idle or no transmission happens, the RxTx line, this line will be at fixed high voltage. And when we are going to send the data from the sender to the receiver, the transmitter will pull the voltage level to low. This is called the first bit or the start bit. Without this, the receiver won't know that it is undergoing some transmission, or else these two bits, these data bits will also be confused with this idle state and will not be considered as data bits. So that is the purpose of the start bit. And secondly, we must make sure that the data transmission rate from the um, transmitter and the data receiving rate by the receiver should be at the same rate, or almost at the same rate, so that the receiver is not too fast or too slow. If it is too fast, we may get garbage values. If it's too slow, you may lack in bits. Okay, let's leave that first. This is there are too many terms coming in the way. So UART can be configured in simplex, half duplex, or full duplex configuration. So what do they mean? So simplex means communication happens from one side to other. I mean, only this device will be able to communicate, will be sharing, this will be just listening. Half duplex means both the devices will be communicating, but only one device will communicate at a time. Full duplex means when this device is talking, this device can start transmitting even when this is transmitting to this. So UART gives full freedom for that, and this is how the frame looks. And for the stop bits, it will be going high and staying there so it meets the idle state. So let's go to the protocol. The synchronous protocol, but so it's one block be done. The SDA of the, okay, I should say SDA is the serial data line, and SCL is serial clock line. Data is transmitted through the SDA. Clock is generated by the master only, not slave. Okay, there is master slave concept in I2C. So you see that the device that can generate a clock is called the master, and the device that cannot maybe is called the slave. So the clock is generated by the master and put it in the CL line, and we must make these connections correctly. And there, what happens is, see, this is the frame for I2C. So for the receiver to know exactly where the transmission has started, we use a start condition. So when the data is not being transmitted, SD and SCL will be pulled up to high. I mean, it will be always at the high state. And when transmission starts, either of this could be the receiver and the transmitter. If it is the master who decides that, like if the when the communication starts, the SDA line will be pulled down while the SL is still high, and the receiver will know that the transmission has started, and this is the slave address. Okay, so multiple masters can be through these two buses, SDA bus and SCL buses. And if the master wants to speak to one slave alone and wants to get response from that slave alone, we must make sure that we specify the slave address so that the slave can respond. And there is the next bit called the read or write bit that says the master wants the slave to read the data that is being sent to SDA, or the slave must transmit the data to SDA. Then is the acknowledgement bit. Now the slave has to acknowledge whether the I2C connection has been proper. If it is proper and it is ready to communicate, it will pull the data line. It will pull the clock line low. Yes. Okay. Is it fine now? Is it fine now? Okay. Okay. Okay, I'll be waiting for some time. Connection is too low. Okay. So, hello. So we are going to start again. So I2C protocol. So it is a synchronous protocol that uses a clock. This is the SDA. Data is transmitted through the SDA and clock is generated through SCL. Master generates clock. It and the master says which slave it wants to talk to or which slave has to talk. So that is the slave address for us, and the read or write bit will say the slave has to read the bit or write the bit, and the acknowledgement bit will be while the slave will pull the SDA low. Only at this point the slave has to do the SDA low, and after that if the slave is transmitting then it will be controlling the SDA, and during then it's the stop bit. So how does the transmission happen like a smooth way? Let's see, without getting lagged. When the when the clock is low, that is where the transmitter will change the SDA or write the bits into SDA, and when the clock is high, that is when the receiver will read the SDA. So everything when something is written over here over this part of the time, in the next part of the time it will be received, it will be read or received. So within one clock cycle, everything will be in proper or in time, and there will be no lag. This happens in every clock cycle. But what if the slave can't process the data within the high time? Then when the clock goes low, the slave can extend the clock line to low for some more time, and can take time to process the bit. So the clock line can adjust its timing based on the slaves and masters. Okay, sure. Okay, this is how the working of I2C. This is all that is there. Most of them are here. Most of them have been already told. Okay, the master devices can't talk to each other. That is a point we must remember. And the slave address is a 7-bit unique address. That's it. It's there for us. Then can Aisha take over this?
So earlier we actually discussed about microcontroller, right? So we learned it's very small chip. So if you look at an actual microcontroller chip, you will notice that it's very small and it have many pins around it. So directly connecting sensors or power supplies, USB cables and all to it is like a bit impractical. So instead of using this bare microcontroller chip, what we usually use is something called a development board. So a development board is like a ready to use circuit. It will already have the microcontroller with all the supporting components, like there will be uh, input output headers will be there will be reset button will be there, USB for uploading programming and power regulating circuits, and everything will be inbuilt to a single circuit board. So we usually use this development boards instead of the bare microcontroller chip. So some of the very commonly used development boards are Arduino boards, ESP32, Raspberry Pi. So there are many examples. So that some examples of development boards. So yeah, Arduino is it's not just a development board. Actually, Arduino is an open source platform, electronics platform. It has both hardware part and software part. Like it provides us many development boards like Arduino Uno, Arduino Nano, and all. So there are there is a hardware part which is provided by Arduino. Then there is software part, like we have an Arduino IDE where we can write our program, compile it, and all. So all this together is called as Arduino. So it is like, I think all of you might have heard at least about Arduino because it's like very beginner friendly. It is what usually beginners use because it's also quite inexpensive. Like it is easy to use, and also it's open source, so it's free to use the Arduino IDE and all. So usually beginners start with Arduino projects. So how it works is like we write a program. So a program which is written in the Arduino IDE is called as sketch. So we write a program in the Arduino IDE, we upload the sketch to the Arduino board. We will be having a USB connection to upload it. Then this board will read the input and everything, and it will process that data and control the output. So that's about Arduino boards. But the disadvantage is actually it doesn't have a built-in Wi-Fi or Bluetooth. So the next development board is ESP32. So comparing to Arduino board, it has a high processing speed, like it's very fast. It has built-in Wi-Fi and built-in Bluetooth. That was the main disadvantage we faced with Arduino boards. But coming to ESP32, we have a built-in Wi-Fi, built-in Bluetooth and all. And it's also low cost and it has high processing speed also. So we already said how what is the architecture of IoT, right? In that connectivity was an important point. So if there is Wi-Fi and Bluetooth, then that connectivity part is also solved. So ESP32 is very suitable for doing IoT projects and all. Then there are many GPIO pins for ESP32. So GPIO means general purpose input output. So these pins are actually not defined whether it is used for input or output. Like we can actually decide whether we should use it for input purpose, output purpose, or like we can decide, right? In our code, when we are writing the code, we can just tell which all pins will be input, output, and all. So it's just flexible, and because of that, it can be used for wide variety of purposes. Then also there is a built-in analog to digital converter. So there are many pins which can read analog signals. So it also helps ESP32 to be used for IoT type projects. Also, ESP32 supports many communication protocol. You already heard about UART and I2C, right? There are many protocols like SPI, UART, I2C, CAN protocol, and all. So all these protocols like ESP32 can support. Like there are many pins, and all these pins are GPIO pins. So it's highly flexible. We can just like decide in the code which pins will be used for which communication protocol and all. So for that purpose, we are using ESP32. Then here I have a small comparison between Arduino and ESP32. So the main difference is Wi-Fi and Bluetooth. I already mentioned about it. ESP32 provides that, but Arduino doesn't have Wi-Fi and Bluetooth. Then the speed, like ESP32 is way faster than Arduino boards. Like here it's 80 megahertz, but here the speed is 16 megahertz. And also ESP32 have high memory capacity. Like there is large memory for ESP32 comparing to Arduino. Also, you can see here it supports communication. There are pins for communication protocols. Like there are more number of pins comparing to Arduino boards. Also, in general pins are also like more. In ESP32, there are almost 36 pins comparing to Arduino's 14 pins. So ESP32 is way more advanced, but Arduino is also like a very good thing. Like it is much more beginner friendly and all. So we already understood like the hardware part, like what all hardware supports. Now, when we come to the programming in ESP32, we know that like every instruction which the microcontroller executes is actually written as program in ESP32, right? Like when to read a sensor data, like what to do with that data, to which Wi-Fi we should connect, when to send informations, to establish communication protocol. All these things we need to write as code into our ESP32. We need to program it. So ESP32 have this advantage also that it support multiple environments. Like we can write code in Arduino IDE, VS Code, MicroPython, JavaScript. So it support multiple environments. So it also gives us a flexibility, right? Now, when we come to programming in ESP32, there are actually mainly two functions. So first one is setup and the next one is loop function. So I already said there are many GPIO pins in our ESP32. So we need to decide each pin for what purpose it will be used, like whether it is used for input purpose or output and all. So if we want to initialize a pin and all, we do it in the setup function. So it execute only once. So this whatever we write inside the setup, it only execute once, and usually it is used for initialization, like we connect to the Wi-Fi and all in the setup function. Then we have loop function. In case of sensors and all, like we need to keep on reading the data, right? For example, if I have a temperature sensor, I need to take the data every 10 second or every 20 second, like whatever I decide. So all these things which need to be looped continuously, like which I need to continuously run, I'll write inside the loop function. So reading sensors, making decisions based on sensors data and controlling the output and all will come inside the loop function. Yeah. So there is attendance sheet in the chat box. So please fill it for attendance. Okay. So yeah, I'll explain some common functions which we'll be using in while writing code for ESP32 or Arduino, whatever. So the first one is pin mode. So pin mode is a function which we use to configure a GPIO pin. Like I already mentioned, GPIO pins. Like we are the one who decide whether it is used for input or output purpose. So for deciding that, we can use this pin mode. So for example, I have the 13th pin. Okay, so I am deciding that my 13th pin will be used for input purpose. So pin mode 13 input command I can give, then it will be used for input purpose. And for output, I can just change the command, and instead of input, I can write output. So for that function, we are using the pin mode. Then we have digital write. So if we have already configured an pin as output, then we can control its state using the digital write function. For example, if my second pin, I have decided it is an output pin. Okay, so I will initially write the code pin mode to output. Then after that, I am deciding, okay, that second pin should get high voltage. Like imagine that output device is a LED. I need that LED to glow. Then I can just write digital write to high. Then that LED will glow. So digital write is used to give value to the output pin. So actually, we only can give digital values. Okay, it can be either low or high because it's digital write. Then we have digital read. So digital read function is used to read the state of a digital input pin. So like for example, I have a variable called state and my fourth pin is an input pin. So I need to store the value I am getting at the fourth pin into the variable state. Then I can just write in state equal to digital read of 4. So if fourth pin is high, then state low. Then we have analog read. It's similar to digital read only, but here we are taking analog values. Here we take digital values. So analog values will be varying in a range. So usually in ESP32's case and all, the range is 0 to 4095. Then we have delay function. So when I was explaining the loop, I said like the sensors will be continuously taking inputs, and there should be a gap, right? Like for example, temperature, I need to measure the temperature every 10 seconds. So for that purpose, we are using the delay. Like we need to stop the program for 10 seconds. Like after one reading, I should not continuously take on reading, right? It's not necessary to take many readings in a single second. So I need to delay my program for 5 seconds or 10 seconds. Then I can just use the delay function. So the default unit is actually milliseconds. So if I write delay 5000, it means 5000 milliseconds, which means 5 seconds. So the program will be stopped for 5 seconds. Then after 5 seconds only the loop will again run. Then I have serial dot begin. So this function is actually to start the communication between ESP32 and the computer. So inside that we will write the baud rate like bit per second and all for synchronizing them. So for that purpose we are using serial.begin. Like it allows us to send message between the ESP32 and our monitor. Then we have serial.println. Okay, so this actually prints the data. Like if I write serial.println ESP32 running, then it will when it reaches that line, it will on the monitor I will get a command ESP32 running. So you can guess from this that for what purpose it will be used. Like we can know if how much the program has run. Like if there is any error and all, it will become easy to debug. So for that purpose we are using serial.println. So this ln actually means after printing this data it will move to the next line. If we don't use this ln, if we just use serial.print, then that cursor will not move, it will be on that line itself. So for moving to the next line, we are adding a ln in the end, so it will move to the next line after printing the data. Then we have Wi-Fi.begin. So ESP32 have built-in Wi-Fi and all. We talked about that. So for connecting to a Wi-Fi, I can just give my SSID, Wi-Fi name, and my password. So I can just write Wi-Fi.begin. My SSID will be the first argument, and the second one will be password. So by this command, I can establish a connection between the ESP32 and the Wi-Fi network. Okay, so that are some common functions which we'll be using while coding. Then, okay, imagine like we are not actually buying all these things, sensors, ESP32, and doing, right. We need to actually do it, simulate it online first. If we directly simulate it on our ESP32 board and all, there are many chances of error. Like if we do a wrong wiring, or if we do some mistake, the cost is like much more. Like what if the ESP32 damages? So it's costly, like it's not worth. Like we should first simulate it online, and we should ensure that there is no error and all, and we should debug everything, and after that only we need to do it on the actual hardware components. So for this simulating purpose, we use Wokwi. So Wokwi is an electronic online simulator. So it allows us to build and test all the electronic circuits inside a web browser. So there will be many development boards, microcontrollers like Arduino, ESP32. There will be sensors inside that. LEDs will be there. So we can use it. We can drag and drop, and we can wire between them and like test it. Okay, I'll just give a small introduction to the Wokwi's interface. So when we open the Wokwi, we can have we can see mainly three areas. Like there will be a circuit area. So this is the place where we will like use the microcontrollers and all, and like there will be sensors and all. We can select it, we can drag it, and we can do the wiring in this section. So this is the circuit area. Then we have the code area. So here we will be writing the programs and all, and then we have the simulation window. Like actually I told about that serial.ln, right, println and all. So it will be printed in this monitor. So okay, so it will be actually printed in this area. So it displays the output and all, and sorry, it prints the serial messages and all. Then we have the simulation window. So after doing all the wiring, after writing the code, if we need to actually run it, then we can press this button. There will be a simulation button, and we can press it, and we will get a simulation window. Like it runs the project, and it will give us the output. So that is about Wokwi. Now we will move to the next topic, and Tejas will handle it.
Hello, is the screen visible? Right. I hope I am audible. So let us go into these commonly used components. So you must know these components before doing anything. So for a good exposure, let's go into them fast, and we have some work later, I mean simulation later. So potentiometer, this is a class 12 electronic component that you have studied, long resistive rod and used to measure battery voltage. So that is that, and but instead we use a different one. We can't have a long rod and all. So we use a circular rod resistive strip and use this wiper, and has a metallic contact, and so that it splits this resistance into two, the R1 part and the R2 part, and this voltage is VR1 by R1 plus R2. That is the voltage, and that is basically a voltage divider. Potentiometer is actually a voltage divider. Two resistors in series across the power source. So it is used for multiple purpose. Like it is a knob actually. You turn this on, and you turn this or rotate this, and you set some level and give some command based on this level to the microcontroller. You can make like have 4 LEDs, and for every 255, I mean every 1/4 of the turn, any one of the LEDs glows. Or instead you can use it for very complicated purpose or very good purpose. So how do we read this by the microcontroller or Arduino is by the ADC that we have already seen now. So the output pin is connected to one of the analog pins. So in Arduino there are 6 analog pins, and in ESP32 we have like 2 sets of ADC1 and ADC2. So first we'll see about Arduino so that you get before going and stepping into other microcontrollers. So this voltage is converted to a value between 0 to 1023. So 0 corresponds to the 0 volt where the wiper is here, and 1023 corresponds to 5 volt when the wiper is here. And any voltage in between, like 2.5 volt, will be 2.5 by 5 in 2023. And I want you to think why it is 1024. I mean, not exactly 1024. Why it is always the powers of 2 that we are using as the voltage to analog to digital converter. We use these 2 powers of 2 in Arduino. There are you can tell if you want. So this is a motor driver. The motor driver is a component that makes the microcontroller to be able to speak to the DC motor. Unlike other components that can easily be controlled by the microcontroller, motor can be a little harder because microcontroller signals are very low powered and low current, have low current and low voltage, but the DC motor itself runs at a very high voltage when there is high voltage and current. So the 5 volt that we supply won't be enough to like turn on this DC motor. It will just stop and won't spin at all. So we use this guy called the motor driver, and it is the intermediary. It will get the input 1, input 2, and the enable pin. Input 1 and 2 will decide in which direction the motor should rotate, and enable will say with how much power should be given to the motor. We'll see more about this in later slides. So the next is the servo. Servo is a type of motor like the DC motor. So what is the difference between the servo and the DC motor? So the servo has a high torque and less speed, less RPM, and while the motor has a higher RPM but lesser torque. So if you're it's very hard to like push the servo, I mean stop the servo going in one direction, or try to turn a servo which is already in the desired angle, whereas it is like a little more easier to do with DC motor. So what is that's how it is in terms of torque. So other than that, how it is more special is by the precision. The angle by which the servo makes is very precise. If I say to move it to 50 degrees or 45 degrees, it actually moves to that degree and it is very precise. Unlike the motor, we can't tell it to move to that level. It actually spins very fast. So how does this do? How does the server do that? It uses a closed loop system. It uses a closed loop system. We give a target position or angle, and it tries to go. It sees its initial position and compares it with the target position and calculates the error and tells it to the controller inside, and the controller will say how much effort the small motor inside the servo should be putting in order to make the error to reduce and go near zero. It also has the gearbox which makes the high RPM turn into high torque. This is the gearbox, the reason for that. And the feedback sensor will measure how much angle the servo is actually in, and and it is used for getting the error from the target position and where we are in. So if you so let us look at a closed loop system with an example if you find it little bit more confusing. So let's say you have a car, toy car, and and it has a microcontroller in it, and you are programming it to go 10 meters straight. uh, in the code you mentioned, turn on the power through the motor driver and give it this much power for this much time and send it. But you did not consider friction and air drags and other obstacles in between, and it didn't actually cross the 10-meter line, but it fell short before that. That is an open loop system, but a closed loop system will see how much far the path it should go and at what position it is currently in, and will make sure that it covers the destination from the current position, so to make the error zero. Its goal is not accomplished till it reaches the destination. It uses the feedback from the sensors to get the current position and uses the target position to get error and so on. So next we'll move to the ultrasonic sensor before it's late. Ultrasonic sensor is used for calculating distance, obvious, and it is used in many of the school projects. So the principle used is same as the echo part. You send ultrasonic sound waves at a very high frequency, and they reflect back to the receiver, and you calculate how much time it takes, and distance is actually time into speed by sound. I mean, time into speed of sound by 2. Okay, because the distance is half of what is the time taken. I mean, time taken will be double of to go there and come back, and you have to calculate distance then divided by 2. It is from the sound chapter, I guess. Okay, but how do we control this? How do we tell it to send shoot pulse? I mean, shoot pulses when we want. So we have this is the trick pin, and this trick pin we have to keep it. Uh, we have to connect it to the microcontroller and pin and connect and make the pin to be in a state high for at least 10 microseconds. And when we do that, the module immediately understands that the microcontroller is telling me to shoot pulses, and I'll shoot pulses, and it will shoot 8 pulses. It is a precautionary measure so that at least one of them will hit the receiver, and it will shoot pulses at high frequency, and it receives the pulses by the receiver. During this time, when the first pulse was shot, the echo pin will turn to high state, and the time duration for which the echo pin is high is the actual time taken for the sound to come back. So that is how the distance is calculated. It's a very interesting concept. So next is the GPS module. The project that you will be doing is will be based on this GPS. So GPS was invented or owned by the US government initially. So no need of okay. The GPS module is used for tracking or locating the position. So how does it do that? So each satellite just broadcasts its exact position and exact time uh, from its position, from its coordinates everywhere, and the GPS receiver that gets this signal, this this is sent through radio waves, and the GPS receiver, when it receives the signal, it calculates the time difference between the current time and the time from that by speed, uh, and then calculates how long it took to arrive. From that, it calculates distance. So the GPS knows that it is at a particular distance x from the satellite. So from one, if we have one satellite, we know that the GPS will know that from one satellite that it is somewhere on the sphere around it. If we have two satellites that the GPS receives, then there will be two spheres, and overlapping them will be one circle. Can you visualize that two spheres will be uh, overlapping over each other, and the common points will be the circle. And when we have three satellites that tells to the that are transmitting, then the GPS uh, will drop down to 2 points. And when we have four satellites, we'll get exactly one position where the GPS is present. So minimum of four satellites should be used to get the GPS, but generally 8 satellites will be used. So this also will deal with it later in slides. This is the LDR sensor. This is the LDR sensor. This is the LDR module. The LDR a module is different from a sensor. Module will contain the sensor plus circuit inside, so that we can get directly the required and desired input from the sensor. Whereas if we have only a sensor, we need to make a circuit ourselves and get the output from it, and process the input and then get the desired state. So this is much easier. So before that, what is an LDR? LDR is a light dependent resistor. It is made up of a semiconductor material called CDS. So what it does is, it is a semiconductor. So electrons are in valence band. When high intensity light with good energy hits this this surface, the electrons from the valence band get pushed to the conduction band, and they become free and conducting. And since the conduction increases, the resistance will drop down. So if you use a voltage divider and check, keeping this as one of the resistors, you will know that the voltage has actually dropped down. This is known as the photoconductive effect, not the photoelectric effect, in which electrons fly off, but here it's used for conduction. Wow, okay. So this is the QR for attendance. Kindly fill this QR. Means scan the QR and fill the attendance. I hope it is done. Next is the H-bridge mode. Okay.
Wait for a minute, pages. Tejas, I think you can continue now.
So as I told, we'll do the H-bridge motor driver now. So it is actually okay. We are going to see about this motor driver IC L293D. That is a H-bridge motor driver. So it has two sides. Each has 8 pins, and each of these sides can run. I mean, can control a motor independently. This side can control one motor. That side can control another motor. So so, so this is what is the H bridge motor driver. Because of its shape, it has got its name. This is the motor, and these are MOSFETs. These two are generally PMOS, and these are NMOS. So for now, consider it as electronic switches. Actually, MOSFETs are more commonly used as electronic switches. So uh, let me tell this once before we go in. To reverse the spin of the motor, we just have to interchange. If this is connected to VCC and this is connected to ground, if we interchange that, if we connect this to VCC and this to ground, the motor spins in opposite direction. Just telling that before we go in. So for forward rotation, what we need is to switch on this switch and switch on this and switch off these two, so that the current flows from VCC through S1 to the motor positive terminal and motor's one terminal, and the other terminal goes to S4 and to the ground. So that the current flow, we want the current to flow from one terminal of the motor to other terminal. We don't want to go in this way. We'll see what will happen if that happens. What we need is a diagonal switches to be switched on. If it is this way, it is the forward rotation, or this way it is the opposite of the spin which we had in this way. When switch S3 and switch S2 is closed, the current flows from VCC to the motor in this terminal, first to this terminal, then comes out through this terminal and goes to this switch and goes to ground. So it is the terminal, it is the reverse direction of spinning in this way. Okay, let us see what will happen if these two switches are closed and these two switches are open. Actually, they are MOSFET. The current goes from here to here and to ground, from VCC to ground. VCC and ground are shorted now. The motor won't have any problem. Like the current won't flow through the motor. The IC will have a problem. Yeah, the the power and the ground are shorted now when S1 and S2 is connected. So we must not do that at any cost. The motor will be safe because no current flows through this, goes directly here. Next is the case where all the switches are turned on. Then then current can't be flown because it is an open circuit. So what happens is nothing happens. The thing is, these voltages will be at some unknown voltage level, and we may not know what that level is. So it may be at high, it may be low, it may be at undetermined state, it may be at any value in between. So the motor pins are said to be coasting or floating actually. So motor is like completely disconnected because there's no current flow into the motor. So this is the GPS module, Max M10S GPS module, which you'll be doing in the project. So what we are going to do now is see how we can read the output of a GPS module. The output is generally as NMEA sentences, National Marine Electronics Association. The national is US. So NMEA sentences. So how do we read these? It starts with the dollar symbol, and the first two letters correspond to the source. If it is GP, it is GPS. For GLONASS, it is GLIS. For GP, it is GPS, the source, and the next three letters correspond to the sentence type. Each sentence type has a different quantity, will not have the same quantities that will be published. different quantities will be output will be given as output from the GPS module. If it is GPGGA, these are the time, the coordinates, the height, the altitude, the precision, all will be there. If it is GPRMC, you won't have height, you will have speed. So each sentence type has different quantities. Next is the 123519. It's a number. Actually, it is 123519. It is the time currently, and this is the latitude. 48. First two digits will be in degrees. The next will be in minutes. 48 degrees, 7 minutes, 7.038 minutes north. And in this part, first three digits will be in degrees, and the next all will be in minutes. It's east, and 545.4 is altitude, and so on. So you see there's a star and some number here that is called the checksum. So if you convert this all into hexadecimal and XOR them, then what you get is this number 0x47. It is like the parity bit used for checking errors, but we won't know where the error is. Okay. So this is simulation time. So we'll start with simple LED projects. So we thought of doing with Wokwi, but the build server load is too high, and it is also ESP32 that we are using. We'll be doing the Wokwi simulation through VS Code, but before that, we'll do simple LED projects first, then go with the communication protocol we discussed. Then we'll see how we can do Wi-Fi connection, and we'll use this website for writing to the cloud. That's it. Okay. First, we'll start with today's plan. Okay. Go to Tinkercad if you have. Go to Tinker. You'll have an account here. Go create circuits. That's it. You got this thing, and you have in the basic part you will have these components only. If you go to all, you will have everything else. So many of them. So first we need to see how we can use, what are the basic commands, how are they used, and what can be done. So this is the Arduino, the first 14 are the digital pins, these are analog pins, 6 are there. The analog pins can also perform the function of the digital pins, but the digital cannot do that of the analog. And these hyphened ones are the PWM pins. Okay. The thing is, we saw in the session start that there will be ADC and DAC, right? But in Arduino, there won't be DAC. There will be a PWM instead. What is a PWM? Like, okay, if I want to output 2.5 volts from the 11th pin, what should I do? What I should do is turn the pin 11 to 5 volt, then immediately go to, after some time push it to 0 volt, assign it to low state, then assign it to high state again, and again to low state with a fixed frequency and fixed duty cycle. If I do that at a very high frequency, 0 volt and 5 volt interchange, you'll get a average. You'll be able to see 2.5 volts in between. Like if you switch on a tube light and switch it off, and you do it at a high frequency, and the time of switch on and time of switch off is same, then you'll see that the brightness of the tube light will be half. Like, instead of lowering the voltage, we just interchange the states at any duty we want, so that we get any voltage that we need. That is the purpose and point of PWM. And analog pins, the 0 to 1093 values that we get is through this analog pins. 0 volt is 0, 5 volt is 1093, and these are the digital pins. This is ground, this is ground 5 volt, 3.3 volt. This is AREF. This is used when the sensors output maximum if it cannot push to 5 volts. If the sensor's maximum output volt is like 4 volts instead of 5, then the Arduino must not confuse that 4 by 5 into 1023 is the number. It is not that. It should be giving 4 by 4 into 1023. That is correct. So we must, for that to happen, we give an analog reference AREF. We connect 4 volts to our AREF, and then the ground of the external supply to ground, and then make sure that this maximum AREF has the maximum voltage that the analog sensor can input through the analog pins. Okay, so first we'll see what are the basic commands. We must know these things before going to something good. So for writing commands, you use /. So we will see how to use digital read, or then digital write, and analog read out, and analog write. So digital read, what it does is it tells the state of the pin we have. It tells whether this pin is in high state or low state. That is digital read. Digital write is if we want the pin to be in high state, we digital write the pin to high state. We write the pin to high state by this command called digital write. And analog read is for these analog pins. You'll get the analog value from a component into these pins, and we read that value through this command. And what is analog pin? It's not related to analog pins. It is actually the PWM pins. If you want to change the amount of voltage, as told before, if you want to half the voltage you want to give, instead of giving it as digital rate high, it will be 5 volt. If you give analog rate of 128, it will be 2.5 volt. Okay, I should say this. The output, if you want this for analog pins, the 0 to 5 volt is converted to 0 to 1023 values. But in PWM pins, we write 0 to 255, that is converted to 0 to 5 volt. So why is that? This is 2 power 8 values, and why is 2 power 10 values? So I think I told you in the start to think why there are 2 powers of 2 here. So let me say that now. So 0 to 5 volt you have. Let me let's say you have 0 to 5 volt. First, what it does is, first it will check with the 2.5 volt level. If the output that, I mean, input that the analog pins are getting is greater than 2.5, it will write a digital binary number with the MSB equal to 1. If the voltage is above the half value, we write the MSB equal to 1, and we check between half and full, and take this middle value and check if the value is greater than this. If it is greater, we write the next digit to be 1, and so on. It goes for about 10 steps from the start, so that you get an accurate numbers and more accurate voltage level. So more the higher resolution, I mean more the 0 to 1020, the more the highest value, the more accurate it will be. Then why are we using 0 to 255 and not like 0 to 4096 or more than that? There is always a trade-off between processing time and also the accuracy. We should, while writing, we don't need much of accuracy to be in matter. We need to be sure of the processing time, but while reading we need more of accuracy. That is the reason. So let's start with the basics of this is the LED, this resistor. So anode is positive, connect it to any pin, let's say 5, connect this to ground. You can change color by this. Go to code. You can name these pins by the component if you want, to which pin you are connecting to, so that be easier instead of dealing with numbers if you deal with text. So as told before, we need two functions that are mandatory in every microcontroller. That's void setup and void loop of. I mean setup function and loop function. Setup is where you set value, initialize UART communication, I2C communication, Wi-Fi. Initialize these pins. You must know which the microcontroller must know which pins we are using. Everything is done in void setup and in setup function, and it will run only once. And in loop function, it runs continuously. After one loop is over, it goes to the other loop again and again and again. So void setup of first. I don't want to initialize serial monitor, so this is the serial monitor. If we want to initialize UART communication or serial communication, we must do serial.begin off, but I don't want to do that. Let's start directly. So pin mode of, what is this, LED, output. The LED is given, we want the pin to be an output pin. Then we go to the loop function. Okay, first we are going to do the digital write part. We want, okay, the output can only do digital write and analog write, that you should know. Read is for the input parts. So it is the output, and I want it to go from in digital write. Okay, what this does is that it makes this pin to go high for 1 second, 1000 millisecond or 1 second, and then makes it to go to low. I did not add another delay. So what will happen is it will go directly into high. So you won't see this to be at a low position. I think you should experience. It is always at high. It doesn't go low because I did not add a delay. It is after instantaneously goes to high. We'll add some delay and see. It goes high to low, high to low, high to low. Okay, that is about digital write function. We don't want this now. We'll go with analog write. Okay. So I told before 0 to 255 is the value we can give. So let's say analog write of LED comma not to 250. Let's see how much it glows. It glows this much. What if it is 128? It glows a little lower. The thing is, like C function or C++, we can also have loops here. What we can do on analog. We need to put delay to see some change here. After 25 seconds, it should be very bright. I mean, at 25, it should be the maximum. And for analog, right, we must put this in PWM pin, that is 3, 5, 6, 9, 10, 11. It is half the value. 255 by 10 is 25. So it should be max at 25 and then go low immediately. Yes. Okay. Now I think you got some understanding of how to do how of the basics of this thing. So okay, I now do analog right off here. Analog read off. This is for rotating. Connect one to ground. Connect one to 5 volt. Change the color. Connect one to here 0. Simple. And one thing to remember, if you do with analog pins, there is no need to input. I mean, there's no need to put in void. Setup of function. Void setup of can be empty. Analog read of what is this pin A0, and you see it. Okay, serial printing. Okay, I'm going to use the serial monitor. The Arduino, the microcontroller and the serial monitor are in UART communication already. So you already witnessed UART here. So serial dot begin of 9600. This is the baud rate and this is the initialization of UART communication. So now what we'll do is serial dot println. So it goes in the next lines. The bad thing about Tinkercad is you won't know which bracket is what. 1023. You change this, you get this value. That's it. Okay. Task 2. The task 2 is basic communication demonstration. Okay, we already saw you. So, we'll take 2 Arduinos now, connect the ground, that's important. First, we'll do this. Okay, what we'll do, okay, motor driver. Okay, we part of motor driver. We'll have a simple demonstration. So put in all the things you have, put all the components. Motor driver you have to search here. That's it. Connect this here. Okay, there are 4 pins, right, in push button. This is the breadboard. This is called the breadboard. These are power lines, and every of this and the horizontal pins, everything is shorted. So if you connect this to any pin here, every pin, everything will be like it has been connected to this pin. So this is also like that. This is for ground. This is for power. This is for power. This is for ground. And these are called terminal strips. And then these 5 pins will be shorted. These 5 will be shorted, but this 5 and this 5 won't be shorted. So that is why we place the IC in the middle. So let us connect this to the ground. Do everything fast. Slow. 5 volt. And why do we need a battery? As told before, the microcontroller cannot control the motor with its what is called power. Okay, so let's go and deep about this my motor driver. It looks so nice. So it has 4 inputs, 4 outputs. This side will deal with another motor, but what we need is to understand how it controls one motor first. So this is the power, and you don't connect it to this 9-volt battery. You connect it over here. Why do we do that? It is this power should be connected to the 9-volt battery. So let's say this power is also a signal power. I mean, so that you know how much maximum the Arduino can give power to the motor driver, so that the enable valves the enable will know that this is the maximum. If I send 5 volt here, the enable, if it is reading 5 volt, then it will convert 9 volt and give the power fully to the motor. This is enabled when we have to connect it to a PWM. We have to use analog right over there. This is input connected to output. This is ground. There are 4 grounds here. Everything is shorted, so connect one this, and it is enough. And we need to make sure that the battery ground and Arduino ground are also shorted to each. I mean, connected to each other, so that both the grounds are equal in voltage. Output 3 go to this, and input 3 to 4. Connection is not over. Okay, fine. TH2R, the UART communication. That's it. Power. Things connected. Okay, let's go to the coding part. So there will be 2 Arduinos. You know which one is which. Go click here. You'll know his name is 2. So we have to put it in here. What we'll do is, if we press this button, this motor should spin faster. If we press this button, the motor should spin slow. That's the very basics of the basic. Okay. So let me. What is this? Nine and 5. Okay. Okay, we'll go with the setup function. Void setup. Since we are going to do UART, we need this CL.begin of 9600. This is the baud rate. Should be same for both. CL.begin is the initialization of UART. Then do pin mode. Now is the difference. It is not input or output, it is input pull up. It's actually an input, but a different type. I hope it is slow, it is easy to follow. So you see that it has 4 buttons, right? So this is connected to this. push button, these two will be connected and these two will be connected. Only when it is pressed, all four will be shorted. Till then, only these two will be connected. Now the ninth pin is connected to this, so it is also connected to this, but it is not connected to anything, so it is actually floating. We don't know the exact voltage of this. It is an unknown voltage. It can be high, low, in undetermined value. So whenever it is not pressed, we make it input pull up. We pull this pin to high state by internally connecting a resistor to VCC and 9 volt. So it is done internally, not connected, but actually it is connected to power through a resistor, so that when it is not pressed, it gets the high state, and when it is pressed, all four are shorted, right? So this pin will have the same voltage as this pin, which is going to the ground. So it will have ground low state when it is pressed, high state when it is not pressed. Why should it have low state when it is pressed? Because we have a resistor connecting this pin to VCC, but this pin is directly connected to ground. So direct connection means direct voltage, but through a resistor means there is some voltage difference there, right? Why? That is the reason we have put input pull up. When it is not pressed, it is high. When it is pressed, it is low. We'll go to the loop function and read these two push buttons value, and we'll do digital read of increase okay, that should be semicolon. Now we need to send it through this thing. I mean the TX to RX line. So we'll send it as a string. Okay. I convert this as a string. It is string concatenation only. These are Arduino strings, not C strings. Then you send it serial.println. Earlier we got only in serial monitor. Now this message will be sent to the next Arduino also. Println of message, give some delay. Okay. Okay. We'll go to the first one. This is good. We have two inputs here and one enable. So earlier we saw that each side is a H bridge and each side will have 4 MOSFETs. Then why is there only 2 inputs and two inputs for the motor driver? What these inputs will do is, it is connected over here and here. This is PMOS, NMOS, PMOS, NMOS. So they'll have gates, okay, gates, and these also have gates. When we put it into low or high state, one of these switches will switch on, other will switch off automatically, and this also the same way. One of them will switch on and other will switch off, because in high state one will switch on, one will switch off. So it is these inputs will be able to control this high and low state of one side of the motor, left or right. Right. So actually it is H bridge, but you have two controls. You must remember that. Where is this input connected to? Input 4 is 7, input 3 is 4, enable is 6, enable is 5. Okay. Now we'll go to setup directly. No, wait. We need a value that must be increasing when it is pressed and decreasing when it is reduced, right? So we need to initialize that also. We'll tell it is 0. We'll go to setup function. Void setup of serial. We need to initialize this here also. Then only the UART communication will work. Then the pin mode as usual. All the three, input 3, input 4, input 5, input 3, input 4 and enable all will be output only. This is input for motor breaker, not input for Arduino. Okay. Whenever a serial message or UART message is sent from this Arduino to this Arduino, it goes into the serial buffer, not this thing. It goes into a serial buffer, we won't be able to see. And we must see if there is anything in the serial buffer or not. So we use this thing. If serial dot available, if anything is available in the serial buffer or not. If it is available, what we should do? We read a string fully. Serial dot read string until what it backslash n. So what it does is, whenever you send a message, you did serial.println, right? So at the ending, you will have backslash n. So read the string fully until you reach the backslash n, then assign it to the string named message. So every line you output, first we did this, right? Serial message. Each line will be now a string and message, not this, but every line will become the message that we want. But the string message that we are sending is this I equal to I value, comma D equal to D value. Now we need to know where what the index of the I is. Index of I. Index of I. What we are getting is this thing, this value. I equal to something, right? We want this value and this value. We don't want this I equal to D equal to comma and all. We are only caring about this string I and string of D. We are going to get that value. For that, first this actually the index is actually set 2. But this function makes it easier than counting it. Right, then we'll get the value. Okay. In I equal to message. It is same as string indexing dot to We are running short of time. Okay. We got everything now. It's actually, I may have made a mistake here. It's actually a character, not a string. It's a string. Okay, no need to take risk. We'll directly do this. Come if message of index I equal to 0. As told, when it is pressed, it will go to ground and it will give the value as 0. Right? What you should do? Index size 0 means you have to increase the PWM. Let's say we increase to 25. Then what if the other button is message published index T equal to 0? What if this button is pressed? You'll get 0, right? Then decrease it by some number 15. Then you can do analog. Wait. But the PWM should be between 0 and 25. If you go on increasing, it might go out of the level. So we need to constrain it. That's clear done. M3, high. We'll keep it in one direction. Don't need to change direction. We can change direction, but we don't want now. That's it. M3 is what is 3. Output 3 yes. So positive only. I mean. Can you see this thing? It has reached its maximum. When I press this button, it goes low to 0. When 0 PWM means 0 RPM. Goes till and goes slowly down. So that is how you use your motor driver. You have to use some battery. The power 1 should be of the microcontroller, power 2 should be of the battery. Don't confuse it. If you do the opposite way, I think you'll get the answer, but in a different way. The value will be half the okay, we have started. Okay, it goes only till 9,000. So it goes only till 9,000. Earlier it went till 16,000. So that is the difference. Okay, we'll go to the third task that is important. Wi-Fi connection and writing to cloud service. Arduino, can't be written in Wi-Fi, so we won't use it. Wi-Fi connection writing to cloud service. We'll use this Wokwi with build server load full. We won't be able to compile it for a few hours, I guess. So no worries. Just a simple function, simple code like the same code. What we'll be doing is, okay, I need to tell you, right? So Wi-Fi connection and writing to cloud, what we'll exactly do is the same, the potentiometer only, basics. The potentiometer will be writing to this website called ThinkSpeak. You create a new channel, an account first, then create a new channel. Write the name of your channel. I have 3 of them, and give the name of the field, the variable which we want to send it here. Then save channel. That's all. That's all you have to do. Let's say I give this field one name. I already have a channel. It goes on dumping all channels. So I have a channel here. Go to API keys. Okay, what is an API? API, okay. What we are going to do is, uh, we are going to make Wi-Fi connection. We are going to connect ESP32 to Wi-Fi, and then we are going to write the potentiometer value that we get from the potentiometer to the ESP32, and the ESP32 will send this value to this let's say this channel through API. What is an API? API is used for writing, for connecting a program with another program. For example, you can say that Zomato or Swiggy or any tracking app that has a map, right? That is actually need not be its own. We can get the map from Google Maps or any other maps, so that it need not have to build the map from scratch, but get its end point, that is the map locations alone, from some other program which is already there. Similarly, there is also weather forecast. We can get the weather forecast report in travel apps from website having weather reports through an API request. What the travel app will write an API request to the weather forecast app to get the weather at that particular point of the day. So API is used for application programming interface, is used for requesting one program to get data from the other program. So it is used for HTTP and HTTPS protocols. So now we are going and writing to cloud using HTTP protocol. HTTP protocol. So this, okay, I'll tell it directly. So this is your okay, not this. This is your Wokwi. When you get into this is your Wokwi part. Go here into your accounts, go to my projects and click new project. But we'll go with this. I'll explain this now itself. So this is the code we are going to use for writing the potentiometer value into the ThinkSpeak. We are doing this since already there's not much time left. So Wi-Fi.h is the Wi-Fi library. We are going to connect the ESP32 to Wi-Fi. The good thing about this is password. The ESP32. Okay. So the HTTP client is another used for. So for every component, okay, I should have told for every component that has so for any of the components there will be different libraries for it, and in every library it will be like an object-oriented programming. So you must name it, name the component, give the component a name or object instance. So let's say I gave it name HTTP. Now I'm beginning the serial communication. So this will be for the serial monitor. Okay, when I start only it comes serial monitor. Next is for the initialization of Wi-Fi. Wi-Fi dot begin off is okay. What are the functions for connecting to Wi-Fi? It is Wi-Fi dot begin off, and for checking the status, it is Wi-Fi dot status of, and for getting the IP address, it is Wi-Fi dot local IP of, and so on. So what this does is Wi-Fi dot begin off will be able to connect this ESP32 to this SSID, that is Wokwi guest, that is already built in this Wokwi, and it has no password. Wi-Fi dot begin off SSID comma password is the function how it is to be written. Wokwi guest is the SSID. There's no password. Then Wi-Fi dot status of. If it is connected now, it will be Wi-Fi dot status of will be equal to WL connected. If it is not connected, it won't be equal to WL connected. So we'll have to wait. Okay, let's wait. Mm, we'll we have to tell that we are no. It needs to. We need to know that it's waiting or why it is not doing these functions. So let's say an indicator is serial dot print hash. So while it is getting connected, it gives hash 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 for every 1 second. So until it is connected, it gives this hash, and once it is connected, we'll get the message connected in the serial monitor and void loop off. So this is the loop function in part equal to analog rate of 34. Okay, these are the pins. I think you can see how much. These are the pins. So 34 is one of the ADC ADC ports, port pins. There's like group of there are two sets of ADCs here, and this one pin in one of the ADC. So analog read of 34 is an analog pin, and these two functions are important. What this does is http.begin off is the function we need to configure this ESP32 to this API. The function this will configure this API to this ESP32.
Can you quickly like complete this topic and like skip the cloud one for today? Like just explain the assignment at the end and like end the session.
Okay.
You need to explain the cloud one.
Okay. Like it is. So okay. If you see the cloud demonstration, it will be easier to understand. So let us do it faster. I think it is the third project. I integrated Wokwi to VS Code. Okay. Like I'll run this alone, right? Okay, it is not running. Okay, we'll go fast into cloud and cloud computing. What is cloud computing? It's the on-demand delivery of computing services over the internet. So, if you don't want to build, if you don't want to have the storage computers and all these things built from scratch, you can rent it from a cloud provider. Who has a data center with thousands of computers and storage area network of millions of hard drives. So what all the services that we can get? We can get the compute power, storage, networking, and analytics. The compute power is from the processing, the CPUs, virtual CPUs, virtual computer CPUs and RAMs, and storage is the millions of hard drives that we have. Networking is mm, how we can network with many servers at the same time. If we are using a multiplayer game, we need to have the data of all the 50 players in the game, and your phone will contain only the storage of you and your account, but the virtual computer will have the storage of all 50 players. So we'll go directly into cloud service models. Mm, there are three types of cloud deployment models: IaaS, PaaS, and SaaS: infrastructure as a service, platform as a service, and software as a service. In infrastructure as a service, you won't get anything. I mean, you will get only virtual computer and storage in it, and the raw storage. You won't get anything. I mean, you won't even have an OS. You have to install OS, you have to install runtime, you have to install database software, you have to put in the database of your website directly into it. Everything you need to do, but you'll get storage and networking. That is an advantage. You don't have to maintain all this physical hardware part. Runtime is actually the Python or Java or anything else. When you code, the CPU must understand it, right? Scaling. What is scaling? So if your website has 5 people logged into it, suddenly 100,000 people are logging into it and seeing, the website would crash. And no, but you have to handle it manually. The virtual computer won't do it. There comes the difference with platform as a service, where OS will be installed, mm, runtime will be installed, database softwares will be there, but there are things that, but we need to do certain things. We need to put in our application code, and we need to manage the app data. We need to put in the database. We need to put values in the database of the users. It won't be doing it automatically, but there's automatic scaling. Like I said before, if suddenly a huge number of people come and view, then what happens is, uh, the app will be duplicated in multiple virtual computers, and the storage will be and no, app will be duplicated in multiple virtual computers, and it won't get crashed. If it is only one computer that has your app running, and virtual computer is different from the physical computer. A physical computer can be divided into multiple virtual computers, and when there is a huge number of population entering your website, mm, the virtual computer gets duplicates your app in multiple virtual computers, so that there is high storage, high processing, and no crashing. Then there is software as a service. This is a full working application that you get. Example: online multiplayer games, YouTube, everything. Mm, what you do is just log in and sign in and use it as you want. The thing is, PaaS example is, you can say Google Colab and Heroku. Software as a service, everything, almost everything is a example for that. Next, we'll have the assignment, but this is based on Wokwi VS Code. I'll give you an online assignment, learn how to do this. Thank you.
Yes, yes, Satvik. I think the presenting is also done, and we are going into the last phase. So assignments will be provided at the group, and you guys can view it and the assignment, and you'll also have a fun game to be provided, which will be shared soon. So thank you for the attending today's first session. We'll have our next session on 10 July at 5 p.m. Yeah, you can stop the streaming. Is it stopped, Satvik?